Hello, welcome to Friday before spring break. I hope that you all have some plans for something this week, not necessarily vacation based, but some either relaxation or getting some work done, or coming out of some I know some rough times for some of you. Maybe things are looking better. Anyway, I wish you well this week. So to get going with that, I wanted to make sure to introduce and talk a little bit about these two activities that are the work for this module. If you haven't had a chance to look at them yet, that's fine. Maybe you'll take a look over break, maybe the week after. Remember, they're not due until after spring break. So you have some time to look at them. This may be review for some of you. This may be new information for some of you. I want to talk about them not only to kind of teach the concepts, but also so that you have a sense of what is expected of you in this class when you do the quiz and like what you're actually expected to know. So we'll start with this one, this mole concept. What is a mole? And perhaps the most important thing about this is that it is just a way of counting things. So this activity will kind of take you through getting used to that, but one great comparison that you can always use is when you talk about a mole of something, it's really the same as talking about a dozen of something. And that's a great comparison because a dozen is something that we all have experience with. And we know that we can count individual donuts, let's say, or we can count dozens of donuts. And we can also count fractions of dozens. You can say half a dozen, or a third of a dozen, or 6.5 dozen, or whatever. But in many cases, it's just helpful to be able to count things in a batch instead of individual pieces. And for something extremely small, like an atom or a molecule, that's absolutely crucial because we can't count individual atoms in the lab. We can't take our tiny atom tweezers and, move them around. So we have to think about them in these big batches. It's really the only way we can deal with them. So that's what a mole is for. It's this very, very large number, 6.022 times 10 to the 23rd. So that's like a 6 with basically 23 zeros behind it. Huge, huge number. And that's because atoms are so small and molecules are so small that to get to the point where we can actually handle them and deal with them, we need an enormous number of them. The reason we have to use this in chemistry, as we'll see in the next activity, is that in order to do reactions and have the reaction come out the way we want, we do actually have to count the atoms. But because they're so small, we need to count them in big batches. And the way that we count things in big batches in the lab is by weighing them, by using mass. So you could imagine this could even be something you do at home. If you have something relatively small and hard to count, like jelly beans or M&Ms or grains of rice, something like that, if you wanted to know how many grains of rice are in a big container of rice, it would take a really long time to count them all out. So what you could do instead is you could say, all right, well, I know how much one grain of rice weighs, and I know how much this entire bag weighs, so therefore I can divide that and figure out how many grains of rice. But depending on your scale, a grain of rice is pretty small. So like my kitchen scale in the kitchen, I can't weigh a single grain of rice on it. But maybe I could say, all right, I know I can count out 50 grains of rice. That's not too bad. I can count to 50. And I can weigh 50. And then I know if I weigh the whole thing, I know how many batches of 50 that would correspond to by dividing. So that's the idea of the mole concept. All right. So as you go through this activity, I would encourage you, even though these questions seem kind of silly, how many trunks are found in 1 dozen elephants? I would encourage you to go through step by step and make sure you understand why they are. And as usual on next time we meet, either Monday or Friday after spring break, we'll go through these answers. But I'll get you started here. So if a dozen is 12. And each elephant has 1 trunk and 4 legs, then 1 dozen elephants would be 12 elephants. And there is 1 trunk per each one elephant. And so that would be 12 trunks total, right? If you've done something called the factor label method of conversions in the past, that's what's happening here. We're going to do a little bit with that, but you're not responsible for that, for being able to do that entirely on your own. So if that helps you, go ahead and do it. If that seems weird to you and you'd rather just sort of think about it, that's fine too. So then if we look at the legs in the elephants, what's changed? We still have a dozen elephants, but now each elephant has 4 legs, so we're going to multiply that by 4. So we can actually take a similar calculation, copy and paste it and move it down here. Our difference now is that instead of looking at 1 trunk per elephant, we're going to look at 4 legs per each elephant. So we end up with 48 legs. So the key here is don't freak out when the numbers get bigger. So after looking at a dozen elephants, we're going to look at a score of elephants, which is now 20. Then we're going to look at a myriad of elephants that is now 10,000. And that's fine. The technique is the same. You're still doing the same thing. And if you need to go back and think about dozen instead, just to kind of keep things straight, go ahead and do that. And then just switch the numbers. Instead of 12, you're going to go with 10,000. Then we're going to move to molecules. Again, the idea of doing these things step by step is so you're not all of a sudden jumping into this unusual or unknown idea of molecules and atoms. You're just looking at numbers. If you don't want to think about the molecules, think about the elephants. Right? So they pick that very specifically so that CH4 is 1 carbon atom and 4 hydrogen atoms, just like an elephant is 1 trunk and 4 legs. So if you want to keep making those connections between the methane and the elephant and the atom, carbon versus the trunk and hydrogen versus the legs, you can keep doing that so that it keeps making sense. And then when you get to these looking at a mole, again, don't worry that it's such a big number. Think about it more in terms of a dozen. What would you do if it was a dozen? Okay, now do the same thing, just substitute the big number. Now, dealing with big numbers with a calculator can be a little tricky depending on the type of calculator that you have. So, for example, I can show you my phone calculator here. So if I pull up the calculator on my phone, it looks something like that. And that might be a mirror image to you. And there's really not a good way of doing that sort of big number like that. I think I can switch to a scientific calculator. Like that. On my particular phone, it still is not giving me great options for doing that. There may be a trick or something, I don't know. But on a typical graphing calculator like you might have, or you can find, I believe you can find simulated ones online. In fact, let me see if I can pull one up here just to show you what this looks like. So here's one. This is NumWorks. And so if I wanted to type in something like 6.02 times 10 to the 23rd, okay, I think I have to go to calculations first. So I would type 6.02, and then they have a little times 10 to the key here, and I can put 23rd in there. And then I can continue. I'm still in the exponent here, so if I want to like multiply it by something, I think I have to move over to the right and then say, times. So if I wanted to know what half a mole was, I could multiply that by 0.5 and get this. Now, oh, my head's in the way here. One thing that you may, I make this, Just hit it. Okay. So one thing that you may see on these and on your own calculators, one shorthand for this idea of scientific notation is this capital E. So I know TI graphing calculators work this way. There is a key on the TI graphing calculator that's capital E, capital E. It's like two in a row, EE. And if you use that, then you don't have to worry about order of operations or like making sure things are in the right order. You could just type 3.01 and then that E key and then 23, and that means times 10 to the 23rd. So that can be a nice way of doing that, doing those types of calculations. So let's do another example here, just so you can see what that looks like. Again, ask questions if you if this isn't clear to you. But if we take one of these, for example, let's look at number 12. How many hydrogen atoms are found in 1/2 mole of methane molecules? There's a lot going on there because we know we have 4 hydrogens per molecule. We know we have that big number, 6.02 times 10 to the 23rd is per mole, and then we need 1/2 a mole. So we go half, we can kind of take this step by step. First of all, what's 1/2 mole of molecules? Well, a 1/2 mole of methane molecules would be half of that big number. And then how many hydrogen atoms? Well, times 4, since just like 4 legs in the elephant, 4 hydrogen atoms. So our whole thing would be something like 1/2 times that big number, and then times 4 because of the 4 hydrogen atoms. All right, so now to put that in our calculator, we could go 0.5 for that 1/2 a mole times 6.02 or 6.022, whatever. There's various, you can use as many decimal places as you want there, times 10 to the 23rd. Oops. To the 23rd, and then times 4. And that comes out as 1.204 E24, which I'm going to write as 1.204 times 10 to the 24. And that would be hydrogen atoms. All right. The second part of this is connecting that idea of counting by moles to using grams. Since we, as I mentioned, in the lab, we have to do our counting by weighing. So we need to know how many grams are in a mole. If we want to count by moles, we need to know how much one of those moles weighs. And the way we do that is by looking at the average atomic mass in grams. And this is what you get from the periodic table. So I don't know if you remember weeks ago when we looked at weighing atoms and numbers of neutrons and isotopes and things like that, I said, ignore those bottom numbers on the periodic table. Those aren't mass numbers that tell you about the number of neutrons. And that's true. What those numbers are average atomic masses. And this is what we use them for. So the average mass in atomic mass units of one carbon atom, we look up on the periodic table. So you can see carbon right above my head here. And the bottom number there is 12.011. And there's no units given, just 12.011. And the reason there's no units given there is because it actually is 2 different units. The average mass of one individual carbon atom is 12.011 atomic mass units. But also, this is one of the reasons that's so useful, also, the mass in grams of 1 mole of carbon atoms is 12.011 grams. So if we're talking about a mole, a whole big batch of 6.02 times 10 to the 23rd carbon atoms, that weighs 12.011 grams. And think about how much that is. That's like a handful, a small handful. So now this becomes an amount that we can actually deal with. We can weigh this. We can scoop it out. We can take half of it. We can take a quarter of it. We can take even a pretty small fraction of it. which before we have to use any kind of specialized equipment besides just a balance. We can also get more than that. What that does, so what this number does is says when you have 6.02 times 10 to the 23rd carbon atoms, we've now brought this in from the tiny, 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 tiny domain into the larger domain of the lab that we can really deal with. All right. Now, when we do that for molecules, all we have to do is add those up for all the atoms in the molecules. So a methane molecule has 1 carbon and 4 hydrogens. So to add up that total average mass in AMUs of that one molecule, we're going to take the 12.011 from the carbon, and we're going to add that to 4 of hydrogen, whatever that is. So let's look that up. And we see hydrogen over there is 1.008. And that's AMUs also. Let me pull up my calculator again. All right, so I'm going to go 12.011 plus 4 times 1.008, 16.043. And that's AMU, atomic mass units. Okay. And then for number 17 here, so then what is the mass in grams of 1 mole of methane molecules? Well, remember that the mass in AMU of one molecule is going to be the same numbers from the periodic table as the mass in grams of 1 mole. So this answer is actually going to be the same. We just make it grams now instead of AMU. All right. And then the calculations get a little bit more complicated here. That's why I've crossed some of these out. So, for the rest of these, I would say give it your best shot. See if you can figure it out. Ask questions if you don't know that, if you can't figure out the answers or you don't know. You can ask your colleagues on Discord. You can ask general questions like, hey, what did everybody get for number 5? Something like that, and just see if you're on the right track. The real key to this whole activity, and the thing I want you to spend the most time and the most focus on, and what we're going to go through again when we come back after spring break, is this number 6. Indicate whether each of the following statements is true or false and explain your reasoning. So here's really what I want you to be able to do. Can you think about these, this idea of weighing versus counting in a qualitative way? So you don't actually have to do, or you shouldn't have to do specific calculations for each of these, although you're free to do the calculations if you want. You should be able to get these answers just by kind of thinking through it and thinking about what does this mean and what does this mean and so on. So if we want to know if 1 mole of NH3 weighs more than 1 mole of H2O, how do we figure that out? How do we think about that? What does it mean? We have 1 mole of each, so are the weights going to be the same or different? Is one going to be more or less? How do we figure that out? So I'm not going to tell you any answers in those right now. We are going to go through them when we come back. But please spend most of your time on this part of this activity. If you don't get the exact calculations, I don't care so much. I want you to see if you can do this kind of stuff where you can really think about it and see if it makes sense to you. All right. If there aren't any questions on that, then we will move to the next activity. A second to get it loaded up here. All right. Everybody see that okay? All right. So once you know some things about moles, we can look at chemical equations. Now, there is a difference between a chemical equation and a chemical reaction, even though we'll sometimes maybe use those interchangeably inappropriately. A chemical reaction is the thing that you physically do, like what you've been doing at home for some of your at-home experiments and so on. That's a chemical reaction. You mix the chemicals or you heat some stuff or whatever, and you make a chemical change. The equation is what we write down to describe the reaction. And so these are examples that you see up here of chemical equations. They express a reaction on paper, and they use some particular symbols that you may or may not be familiar with. Hopefully by this point you're familiar with chemical formulas. But there's also some other things going on. There's some numbers, there's some letters in parentheses. And so working through this activity will help you to understand what those things are all about. So let's talk about them a little bit. So first of all, what's happening with these numbers? Let me grab a new page, sorry. All right, so let's say I just wrote this first equation just using the chemical formulas like this. Now, this is a real equation. This is a real process that occurs. You can take hydrogen and oxygen. You can give them a little spark. They release a lot of energy, and they make water. Now, there's a problem with this reaction, and this equation, not reaction equation. There's a problem with this equation, and the problem is that if we really look at what's happening at the molecular level, something is missing. So let's express these in terms of their Lewis structures. Hydrogen is just HH like that. Oxygen is OO like that. It's got double bonds. And then water is HOH. All right. So if you think about these atoms physically actually like combining, doing their thing, you see a problem. And the problem is that one oxygen is missing in the product. So if you imagine these as actual models or like little toys, you could take the two hydrogen atoms, the two oxygen atoms, you could pull apart the hydrogens, pull apart the oxygens, reconnect the hydrogens to the oxygen, but then you've got this leftover oxygen. And that's a problem because the law of conservation of mass or matter says that matter can't be created or destroyed in a chemical reaction. So what happened to this oxygen? Well, there's a couple choices here. One thing is maybe we just didn't say that it was there. Maybe there's an extra oxygen atom. But that's not right because, like I said, this is a physical process. This is a real reaction that happens. So if extra oxygen atoms were being formed, we would see them. We would know that. So we can't just add extra atoms to our reaction. All right, well, maybe we need more oxygen in the product. Maybe we make this H2O2 instead of H2O. Well, that doesn't work either because H2O2 is a totally different molecule. H2O2 is hydrogen peroxide. If you've had any experience with hydrogen peroxide, it is not the same as water. Definitely not the same as water. So that doesn't work either. We can't just make a new molecule. So a couple lessons from this when we're talking about balancing these reactions. One, we can't just add more stuff. The reaction or the equation that's given is the equation. That's the reaction that's happened. We can't just add more pieces onto it because that doesn't happen. And then secondly, we can't ever change the subscripts, the little numbers. Because when we change the subscript, we change the identity of the molecule. We make a different molecule, and that's not what's happening in this reaction. The equation has to represent the actual reaction that happens. So if we can't just add extra atoms, add extra numbers, things like that. So what do? How do we bring these things into balance without altering those things? And the answer is we change the ratio by which the reactants react and the products are formed. So if instead of one hydrogen molecule reacting with one oxygen molecule, we had two hydrogen molecules reacting with one oxygen molecule, and then we make two products, we haven't changed anything about the reaction, about the process that occurs. We're just recognizing that the ratio by which these react is 2 to 1 instead of 1 to 1. And the way we express that in the equation is with these numbers out front known as coefficients. So we put 2's in front of the hydrogen and the water to show that it reacts in a 2 to 1 ratio and that 2 molecules of water are then formed. So that's what these numbers out front mean, and that's how we balance chemical equations. All right, so now going back to here, let's actually balance some equations. And I'll let you work through the rest of it that talk about like bowls versus numbers and how you kind of deal with those numbers. I think you can figure all that out. But I want to show you the actual procedure for balancing equations, because while this works for very simple ones where you can just kind of look at it and go, oh yeah, I need one more of those, when they get a little more complicated, that no longer works. So let's talk about how to balance equations in a systematic way where you're like working through it in a way that makes sense. So we'll take this equation. And I'm just leaving those phases out for now, the things in parentheses, just so we can focus on this. This is combustion of propane. So this thing on the right, on the left is propane. And we've got a lot of stuff going on here. There's lots of different types of atoms and things. So how do we balance an equation like this where it's not, oh, hold on. I wrote something wrong here. How do we balance an equation like this where it's not immediately clear which number we need to put where? The way we do this is first, you need to count the atoms on each side of the equation. So the equation needs to be balanced from the left side to the right side. So that means we need to think about all of the atoms on one side versus all of the atoms on the other side. So I'm just going to count them up. On this side, I've got 3 carbons, 8 hydrogens, and 2 oxygen atoms. And then on the right side, I've got 1 carbon, 2 hydrogen, and 3 oxygen. So I get the 3 oxygen because I'm adding the 2 from the CO2 and the 1 from the H2O. All right, so then I've got my counts. Looks great. And I can see that they're not in balance. This is a good first check because sometimes the equation just is balanced as it is. All the coefficients are 1 and we're good. In this case, that's not true. There's carbon changes, hydrogen changes, oxygen changes. So we need to make some changes to the coefficients to bring these numbers in line. All right, so let's do that. Now, what do you start with? Well, there's no good answer to that. You can kind of start wherever you want. One nice rule, though, to make sure you don't get thrown off is if there's any atom that appears in multiple different molecules on one side of the reaction, save that till the end. So in our example here, oxygen, if I said, okay, let's start with oxygen. Well, we've got 2 on this side, we've got 3 on this side, which means we have to change here and we have to change one of these, and that may not actually work out because there's just too many different things that have oxygen in them. So we're just going to leave that. It's not always oxygen, but we want to leave the one that's in a bunch of different species till last. So we can start with either carbon or hydrogen. Doesn't matter. I wrote down carbon first, so we'll start with carbon first. We've got 3 on the left and 1 on the right. And now we want to think about how should we change the coefficient so we have the same number on both sides. So don't think about how many you have to add, because we're not really adding them. We just want to know how many total do we want. And then the total number we want on this side is 3, right? So that they're both 3. And to get 3 on this side, we need to put a 3 here as a coefficient, and that gives us 3 carbons. Now, the next part, very important, is you have to correct the rest of what you've changed also. So when we put a 3 in front of the carbon dioxide as a coefficient, not only have we changed carbon, but we've changed oxygen as well. So now instead of 3 oxygens, we have 6 plus 1 is 7. All right. So now we have our carbons in balance. We can move on. So we're going to move to the hydrogen. 8 on the left, 2 on the right. So again, we want to know what can we do to make sure we get 8 on the right. And to do that, we're going to put a 4 as a coefficient, because if we have 4 water molecules and each has 2 hydrogens, then we have 8 hydrogen atoms total on the right. So that works out, but we can't forget we got to also correct because we've changed our oxygens now. So now we have 6 plus 4, which is 10 oxygen. So now finally we can move back over to the left, and we can add, or we can say, okay, we've got 10 oxygens on the left. Or on the right, we want to get 10 on the left. So to do that, we put a 5 over here. And now we can check, we can look at our numbers. We've got 3 carbons, 8 hydrogens, 10 oxygens. If everything balances, meaning you've got the same number of everything, then you've balanced the equation. You're done. You've done it. The only exception to that is sometimes you end up with multiples. So, because of the trial and error involved in trying different numbers, you could potentially end up with 6 carbons, 16 hydrogens, and 20 oxygens. That's still balanced, but we usually like to divide and get the lowest possible coefficients. So you would just do that at the end, if that's how that came out. All right, and that's how you balance an equation. Okay, I want to show you one more similar equation, but that ends up kind of causing a problem, and we can see if we can figure out how to fix the problem when we get to it. So this time we're going to look at butane, C4H10. And so the process at first is going to be the same. We write our equation, and we start counting up our numbers. So we've got, on the left, we've got 4 carbons, 10 hydrogens, 2 oxygens. On the right, 1 carbon. 1 carbon, 2 hydrogens, and 3 oxygens. All right, and now we can start our balancing. So 4 carbons on the left, 1 on the right, so we'll put a 4 here. And that way this can change to 4, and we now have 9 oxygen. For the hydrogens, we've got 10 on the left, 2 on the right. So we'll put a 5 here. That also changes our oxygen. Now we have 8 plus 5 is 13. And here's where we run into a problem. So 13 oxygens on the right and 2 on the left, but any number we put in here is going to give us an even number of oxygens because we're always multiplying by 2. So there's no way without putting a fraction here or something that we can get this to balance, because we can't ever get 13 oxygens on the left. We can't make something times 2 equal 13 when we're counting in whole molecules. So this is something that comes up fairly often. So there's a good strategy to do this. First off, there's always trial and error involved in these. So you could just start trying some different numbers and see what you get. But it's always best to work systematically rather than just randomly. So rather than just randomly trying numbers, let's think about how we can purposefully make this work. And one way that we can do that is by just doubling everything. So if you have an odd number and you double it, you get an even number. And if we double everything, we keep the ratios the same, so we don't have to go back and rebalance everything. So let's just leave, we'll leave the oxygen open for now because we know we're going to have to mess with that later. But we can double everything else. So we can go 2 of these, which gives us 8 and 20. We can go 8 of these, which gives us 8 and 10 of those. So sorry if all my crossing out is getting messy. I wanted to show you where we came from, so I don't want to erase what we already did. But by doubling everything, now we have an even number of oxygen, And so therefore we can balance this. So 26, if we want 26 on this side, that means we need 13 of these molecules. 13 times 2 is 26. Whoops, not 13, 20. All right, 26 oxygen. All right, and so there you go. That's how you would do that. Now, so if this comes up, if you kind of get things balanced and then you realize, uh-oh, there's no way I can fix this, try doubling everything and see if that makes it work. Other things you can do, sometimes you get in the situation where you keep going back and forth and you balance one side and that makes the other side get messed up, so you balance that, and that makes the other side messed up, you balance that, and that makes that mess up, and so on. Generally, that's an indication that maybe one of the numbers is actually wrong, like you copied a subscript wrong, perhaps, or you wrote down something wrong or forgot one of the reactants, or you messed up on your multiplication. So if that starts happening, go back and check your numbers or just erase everything and start over. Another reason for that is that you left the wrong atom till the end. So go back to the beginning and start by balancing a different atom instead. So let's say we started with carbon and we couldn't get it to work out. We can go back to the beginning and start with hydrogen instead and see if that works better, or oxygen, or whatever. So you can try that in some different ways. There's not a whole lot of extra practice on this document here, but in the chemical reactions virtual lab, there is a lot of practice doing this. So that would be a good thing to do, particularly before you take the quiz. Make sure you go through that chemical reactions lab and practice balancing all those equations. And if you have any questions or you're not sure if you got them right, just ask, and I can either just tell you if it's just a couple, or you can just say, hey, can you go through numbers whatever through whatever in the next live stream, and I will do that. And yeah, any specific questions, send me messages on Discord or through email, and I'll try to keep track. And then when we come back on Monday, I'll try to go through and answer all the questions that you had, or things that you wanted to check. All right. So if there aren't any further questions today, that'll be it for us. I'll hang around for a second in case there are questions. Take a look at Discord. Otherwise, I will see you after the break. I hope you all have a great break, even if it's not a break in terms of like a vacation or really a break from life, but at least a break from classes. All right, I'm not seeing any questions, so I will say goodbye for the week, and I'll see you back on that Monday evening after spring break. Bye, everybody.